Mount Rainier is considered to be an active volcano seismically, but scientists say right now people are misinterpreting data and what they're seeing is not a sign of a blast.
Mount Rainier.
Mount Rainier.
Mount Rainier.
Mount Rainier.
This is the situation as it stands today. Over the course of only a few days, the Pacific Northwest, a region renowned for its lush landscapes and sky-piercing volcanic peaks, has become the focus of unprecedented scientific scrutiny. The warning did not originate with local agencies alone. It was NASA, the world's leading eye in the sky, that issued a rare and unmistakably urgent red alert, sounding alarms for the region as a whole. Their satellites captured a startling picture of movement, the flanks of volcanoes subtly swelling, fractures stretching wider, and the landscape itself shifting with an uneasy rhythm. Ground sensors and seismic networks revealed a narrative of their own. Coordinated strain migrating along ancient fault lines outlined beneath the forests and peaks. Scientists describe this emerging phenomenon as tectonic tearing, an invisible yet tangible signal that the land beneath the Pacific Northwest was entering a fresh chapter of unrest. For the first time on record, a Level 5 volcanic alert was declared for this sector of North America. This classification, reserved for only the most extraordinary circumstances, has left scientists, emergency planners, and residents searching for answers. Is the region on the brink of transformation? What might these waking giants on the edge of the continent be capable of? Is this a fleeting episode of turbulence, or a signal that an age of calm could be ending? As we explore the evidence and warnings, we stand at the intersection of drama, discovery, and uncertainty. In this broadcast, we follow the path of tectonic activity, satellite imagery, and ground truth to ask, could the volcanoes of the Pacific Northwest be entering a period of unrest? And what could it mean for life in their shadow? Chapter 1. Cascade Awakening, the Red Alert Unfold. It began almost quietly. Across the Cascade Heights, where peaks like Rainier, Hood, Baker, and the formidable underwater Axial Seamount dominate both the myths and maps, scientific monitoring has always been vigilant, tuned to the faintest sign of restlessness. Yet the data of 2025 marked not just a new season, but a transformation. NASA's network of satellites, capable of measuring surface movement and signs of underground activity, began to detect indications of ground swelling and possible magma shifts. A region responding to internal pressure, its breath visible in the slow, broad movement of mountains. Direct evidence soon followed. Bulging flanks on several of the most renowned peaks in the Cascade Range. Ground deformation data showed parts of the crust swelling, accumulating energy from below. To the naked eye, the forests and snowfields remained unchanged. Yet to the relentless gaze of satellite, a tectonic pulse was becoming clear. A subtle quickening in places considered dormant or merely restless. On the ground, the Pacific Northwest Seismic Network logged its own set of anomalies, capturing small shifts in the rate and pattern of quakes, scattered tremors suggesting magma migration below the surface. While much of this activity was modest, quietly clustered around Mount Rainier and scattered elsewhere, the organized nature of these shifts caught the collective attention of experts. This was not merely chaotic activity, but something with the signature of coordination. The term coordinated strain began to enter the scientific lexicon. Fault systems in different locations showing similar patterns, as if responding to a common geologic script. Against this backdrop, NASA, reviewing the satellite records and a mounting pile of ground observations, elevated its alert level. For the first time, a Level 5 volcanic alert, coded red, the rarest and most consequential in volcanic risk protocols, was declared for the Cascade region. The significance of this moment was not lost on observers. Historically, volcanic warnings in the United States have been measured, advisory, warning, but rarely at their highest. Level 5 is reserved for extraordinary, widespread geological unrest. It signals not only the possibility, but the real likelihood that a significant portion of the regional geosystem is behaving in unprecedented fashion. The announcement reverberated through scientific agencies, media, and local communities alike. What precisely had forced NASA's hand? Were the volcanoes of the Pacific Northwest indeed stirring in a way never seen before? Or could the sophisticated sensors be misreading the landscape's natural background noise? The answer would come only from a careful synthesis of evidence. Chapter 2. Tectonic tearing, the mechanics of unrest. What is it that prompted the unprecedented red alert? To answer this, we peer beneath the landscapes of the Pacific Northwest, to the processes invisible to all but instruments and experts. Tectonic tearing, the phrase on every scientist's lips, differs from a typical earthquake, which is a relatively brief, sharp release of stress. Instead, tectonic tearing is a process in which pressure is not released in a single burst, but slowly redistributed. Segments of the Earth's upper crust strain, stretch, and slowly move, possibly for weeks or months, accommodating changes that sometimes precede something larger. The indications: fractures widening, flanks bulging as if inflated from within, and magma creeping toward new and potentially weaker regions. Unlike the activity centered on one volcano, tectonic tearing can occur over a whole region. Satellite images in 2025 showed faint lines of uplift and displacement across the Cascades, evidence of crustal movement, subtle yet significant enough to warrant attention. Some bulges, invisible except to the most rigorous instrumentation, could be mapped stretching for miles. At the same time, some long-standing fractures began to widen measurably. Sensors tracked these changes, sometimes down to the millimeter. Many followed geologic lines beneath peaks like Rainier, St. Helens, Baker, and the enigmatic Axial Seamount. Others marked changes along the bases of volcanic edifices. Magma was the likely driver. Deep underground, molten rock was shifting, gradually pressurizing overlying structures. Rather than a drumbeat of constant, high-magnitude quakes, the region experienced a slow-motion deformation, massive tectonic and volcanic bodies flexing and testing their boundaries, responding to complex histories and present tension. Seismologists monitoring the Pacific Northwest Seismic Network used the phrase coordinated strain with increasing frequency, describing a potentially rare connectedness between fault systems that, in more typical times, would behave independently. This suggested an unusual scale of regional response. What does tectonic tearing mean for the millions living below these peaks? History teaches that large-scale deformation can precede eruptions, or simply mark the start of new cycles of underground reorganization. The migration of magma beneath the surface raises the possibility of future volcanic activity, though neither its timing nor magnitude can be confidently predicted. Is the Pacific Northwest flexing and realigning in routine fashion, or preparing for more consequential change? Chapter 3. Volcanoes under watch, the giants of the Northwest. In this story, no individual volcano stands as a single focal point. 2025 has seen the giants acting in chorus. Yet certain mountains draw special attention. Mount Rainier is both a cultural icon and one of the most watched volcanoes in the United States. Its summit and broad flanks are impossible to ignore. Yet it is the restless machinery beneath that warrants the closest scrutiny. Widely considered America's most dangerous volcano, any changes here echo far beyond the immediate valleys. In July 2025, Rainier experienced a brief earthquake swarm, a summer spike in seismicity, which then returned to usual rates. Scientists labeled this later activity typical, yet any tremor during a period of tectonic tearing and a level 5 red alert was closely analyzed. Meanwhile, beneath the Pacific, attention was drawn to the Axial Seamount, an immense underwater volcano rising from the Juan de Fuca Ridge off the Oregon coast. Axial Seamount, although hidden from view, is one of the most active submarine volcanoes in the world. Monitoring by scientists has suggested it could erupt as soon as 2025, based on ocean floor movement and pressure measurements. This possibility gained renewed significance as signals converged across both land and sea. Seismic equipment worked around the clock, and satellite imagery was updated daily. Researchers and officials faced the challenge of distinguishing meaningful alerts from the glut of normal background shifts. In this climate, there were measured voices providing reassurance. There's no cause for alarm, no interesting seismic activity, and no increase in earthquakes on the mountain at this time, stated one expert, highlighting the challenge of communicating risk during periods of intense observation. Nonetheless, with a NASA red alert in force, even reassurances could offer only partial comfort. Could the region's volcanoes simply be cycling through normal fluctuations? Or did this represent the beginnings of something that would alter the region's history? Chapter 4. False alarms and real dangers, interpreting the signals. In a region like the Pacific Northwest, the line between real crisis and false alarm is extraordinarily thin. This was especially apparent after NASA's announcement. The Pacific Northwest Seismic Network, rushing to process a surge of new signals, initially registered what appeared to some as evidence of earthquakes directly beneath highly hazardous volcanoes. News feeds and scientific forums were quick to amplify the reports. Was an eruption imminent? Or was this the land's slow shift misread as catastrophe? Within hours, authorities clarified that no significant changes had in fact occurred. The apparent seismic signal was the result of technical misinterpretation, instrumental noise, not volcanic commotion. Experts confirmed there's no cause for alarm, no interesting seismic activity, and no increase in earthquakes. Still, the false alarm did little to settle nerves. The indicators of tectonic tearing, swelling flanks, and the ongoing red alert remained unaddressed by the incident. The event highlighted the difficulty of interpreting signals in a seismically restless zone. Networks designed to relay warning can be overwhelmed by both real and imaginary signals, leaving both scientists and public suspended between reassurance and anxiety. The lesson was plain. In a place as restless as the Cascades, the absence of immediate chaos does not equate to the absence of risk. Each cycle of warning and clarification demonstrates how quickly things could change. While recent alarms may have failed to predict an immediate crisis, new cycles of magma and tectonic movement do not pause for error. Could the next episode be the true precursor to significant activity? Chapter 5. The Underwater Giant. Countdown at Axial Seamount. While the region's most recognizable volcanoes drew the headlines, a less visible yet equally crucial part of the drama played out beneath the Pacific Ocean. The Axial Seamount, perennially active and closely watched, emerged as the player most likely to deliver on the warnings of unrest. Perched on the ocean floor off Oregon, the Axial Seamount summit is nearly a mile beneath the waves, its vast volcanic expanse hidden from direct view. Axial's activities have long been tracked by ocean bottom sensors and remote satellite measurements. In 2025, this instrumental web began recording a now familiar sequence: measurable ground uplift, subtle shifts in subsurface fluids, upticks in seismic tremor. For marine volcanologists, such changes are classic precursors of eruption. Based on its past history and most recent readings, scientists agreed that eruption at Axial Seamount was likely in the near future, possibly even before the year's end. The implications extend beyond Axial alone. Submarine eruptions do not typically produce dramatic plumes visible from land, but they have the power to reshape the ocean floor, influence regional water currents, and in certain cases, generate tsunamis. The 2025 signals did not directly indicate potential for catastrophic tsunami, but the broader unrest at Axial forms part of a tapestry that connects land and sea in the region's risk profile. Does the accelerating pattern at Axial reflect the same coordinated strain as on land? Oceanographers and geologists alike continue to pore over the connections, weighing possibilities while recognizing that much about the linkages between these vast systems remains undiscovered. Chapter 6. The historical context, volcanic cycles and human risk. The dramas of 2025 do not arrive without precedent. The Pacific Northwest sits atop a complex and ancient geologic system, forged over millions of years by cyclical eruption and retreat. Its valleys and lakes, its cliffs and riverbeds, are shaped by deep volcanic time. What separates the current moment is the simultaneous convergence of multiple lines of evidence, paired with technological capacity to observe those changes in real time, and a red alert unprecedented in modern record. Previous generations witnessed catastrophic activity. Mount St. Helens' 1980 eruption remains the region's most infamous modern disaster, sending ash thousands of miles and destroying vast tracts of landscape. Thousands of years earlier, a reminder of the scale of transformation inherent in these peaks. Yet even these monumental events were preceded by warning signs experts now recognize only in hindsight. Today's network of satellites, ground arrays, and ocean bottom stations delivers an unprecedented density of data. Each subtle uplift, fracture, and change in activity can be mapped, analyzed, and reassessed almost in real time. This is both a blessing and a curse. It keeps experts constantly vigilant, but also leaves the public vulnerable to false alarms. Overlaying this is the question of human risk. The Cascades are home to millions of people, dense cities, and crucial infrastructure, all winding their way through valleys shadowed by volcanic summits. The cost of both false reassurance and unnecessary panic is high. The balance between urgency and calm is constantly calibrated. The NASA Red Alert, therefore, is not just an act of scientific caution, but a symbol of our technological readiness and our underlying vulnerability to the forces that have always shaped this region. Chapter 7. Science and Uncertainty, where data meets doubt. The events of 2025 have challenged every assumption in geologic monitoring. From satellites orbiting hundreds of miles above to antennas planted deep in the earth and robots crawling the ocean floor, data is amassed in quantities never before seen. Yet the problem remains: how to separate true threats from the noise of natural background activity. Does a cluster of earthquakes beneath Rainier truly hint at disaster, or does it reflect the volcano's routine settling and shifting? When multiple seismic networks detect subtle but widespread strain, are we witnessing an interlinked system approaching criticality? Or is it coincidence shaped by improved sensing? Coordinated strain captures both the uncommon scale and the broad uncertainty of the current situation. That fault systems and volcanoes across a vast region could begin to move in parallel is statistically rare, yet the observations continue to stack up. Nevertheless, officials and scientists balance vigilance with caution. Volcanic behavior is inherently unpredictable, with processes that can unfold over centuries before reaching a breaking point. Even the most advanced satellites and arrays cannot conclusively determine where or when the next eruption might strike. The Level 5 Red Alert is less a prediction of disaster than an acknowledgement that something exceptional is underway, a convergence of signals that demands our close attention. Scientists remain deliberately measured, striving for public transparency without fueling panic. Emergency management officials bear the responsibility of readiness, even as they admit the systems they hope never to use rely on assumptions always subject to revision. Chapter 8. The Human Factor, Living Under Warning. Behind the scientific drama are the lives unfolding as normal across the Pacific Northwest. Millions live in the shadow of volcanoes that have shaped both landscapes and communities for generations. Trails cut across ancient lava flows. Rivers carve courses through valleys marked by ash and old pyroclastic debris. In 2025, the alert brought heightened vigilance. News of NASA's Red Alert and continual scientific updates, sometimes couched in technical language both urgent and uncertain, formed a new background reality. Schools revisited emergency protocols. Hospitals assessed evacuation routes. Local governments, many managing with limited resources, found themselves clarifying risk while attempting to bolster preparedness. Yet, daily life did not stop. Trains still wound their way past the flanks of Mount St. Helens. For many, the threat remained remote, felt more in abstract than in daily hazard. And for others, words like tectonic tearing, coordinated strain, and red alert became part of the new landscape of uncertainty. What then does readiness look like in this volatile setting? For public officials, it means strengthening monitoring networks, refining early warning systems, and cultivating clear channels of communication. For families and individuals, it means maintaining basic preparedness, emergency supplies, evacuation plans, awareness of local hazards. The sense of living in the crosshairs of potential unrest is both concrete and distant, a function of geography, time, and the unpredictable rhythms of the land. Chapter 9. Toward the Unknown, the Red Alert in Context. As immediate alarms begin to fade, at least for now, attention shifts to the unknown stretch ahead. The Axial Seamount is watched for signs of eruption, its signals replayed daily by oceanographers. Swelling and widening fractures on land may quiet or may signal further cycles of activity, remain restless under vigilant observation. Their hidden systems cycling in ways barely glimpsed even by the most advanced of sensors. The scientific community stands ready for whatever the data may bring next. The intersection of tectonic tearing, volcanoes bulging, and a Level 5 volcanic alert becomes not only a focus of local caution, but a global case study in how to respond to signals at the limits of current knowledge. Researchers will continue to revisit each alarm, reassess every line of evidence, and refine the tools for detection. For the public and the world beyond, the lessons are about scale and humility. The Cascade volcanoes have lain mostly quiet for generations, but their history is anything but still. NASA's Red Alert, rare as it is, reminds us of how much we know and how much still surprises. Are we witnessing the approach of a new cycle, or simply the planet's natural, unpredictable conversation with itself? These questions for now remain open. The Earth's signals, clear, ambiguous, sometimes contradictory, demand both our attention and our adaptability. In the end, the episode of 2025 is inscribed not just in warning levels and streaming data, but in the overlap of vigilance and unknowing. The volcanoes of the Pacific Northwest have awakened to the watchful gaze of science, if not to eruption. The ground has flexed, the systems remain alert, and the rarest of alerts underscores the unfinished story beneath the mountains and under the sea. As ever, the restless Earth keeps its secrets. Each day brings new data, further questions, and continuing reasons to watch and prepare. The mountains, silent for now, and the underwater giants, unseen, continue their concealed dialogue. The world waits, alert, informed, and still uncertain, wondering not only when but how these giants will speak next.